So let's talk about timing. We've talked about timing of combinational circuits. Timing of sequential circuits is tied to the timing of a D flip-flop. So one of the main stipulations is that D, the input to a flip-flop, has to be stable when it's sampled. Otherwise, we're going to get either a value that's not valid or a longer delay. So it's similar to a photograph, right? If we have our flip-flop, this input, when we sample it, right, when we get this clock edge, this input D better be stable. Otherwise, we're going to get a blurry or, bad output. And so these constraints on our flip-flop, we can divide them into input timing constraints and output timing constraints. So the input timing constraints are, well, input D has to be stable around the clock edge. And particularly, it has to be stable a setup time before the clock edge. So this is the time before the clock edge that D has to be stable. And this shows either 1 or 0, doesn't matter which one, but it has to be stable, not changing, a setup time before the clock edge. And then after the clock edge, it has to be held stable for at least a hold time. So it has to be stable during this entire period around the clock edge. And these hash lines mean that D can change at other times. But it has to be stable around this clock edge. And the sum of setup and hold we call the aperture time, similar to the aperture time of a camera, where the aperture would open and then allow the picture to be taken and then close. So this is setup plus hold is also referred to as the aperture time, or T sub A. And so let's think about where these come from. Well, let's dive into what the flip-flop is. Remember, a flip-flop is 2 back-to-back latches, L1 and L2, and here we have our clock. And so where is the setup time? Well, the setup time, we're clock going from 0 to 1. Here's our clock edge. Clock going from 0 to 1. That's going to occur, right? Our clock going from 0 to 1 here. When that happens, we need to make sure that this internal node N1 has a stable value, right? That it's not changing. So that setup time really is the time it takes for D to get into that internal node and have a stable value. So T setup is that physically, from the circuit itself, it comes from the time it takes for D to get into the internal node N1. And then when the clock goes high, clock goes from 0 to 1 now, and 1 can travel through the second latch L2. And let's think about the hold time, where the hold time comes from. Well, hold time is, well, when the clock goes from 0 to 1, right, when we get that clock edge right here, our data is going to go through here. But actually, when clock goes from 0 to 1, clock bar, right, this is clock bar that's driving L1. Clock bar doesn't go to 0 until a short time later. What's that short time? Well, it's the delay of that inverter. So really the delay of that inverter is the hold time, because it says, hey, D can't change because actually D is still getting sampled after the clock edge until that latch gets shut off a hold time later. And so we can see where these values come from by looking at the internals of the flip-flop. We have T hold, the time it takes to shut off L1, and T setup, the time for D to get into the internal node N1. Now we can look at the output timing constraints. The output timing constraints are how long after the clock edge that the output Q changes. And so remember that we now have our data, or our Q, our output Q, changing according to the clock edge, not D, right? D changing will not change the output of Q until we get a clock edge. So we call this propagation clock to Q. So from the clock edge to Q, output Q changing. So propagation clock to Q. So this is like in combinational logic, propagation delay was the maximum delay. Propagation clock to Q is the maximum time after the clock edge that Q will change. And contamination clock to Q, TCCQ, is the minimum delay after the clock edge that Q will change. And again, we can dive into our internal circuit of our flip-flop. We have clock and clock bar and our two D latches, L1 and L2. And when we get a clock edge, clock goes from 0 to 1, get that clock transition from 0 to 1. Well, it still takes some time for Q to change, and that's this delay here. Propagation clock to Q is the maximum delay of L2, and contamination clock to Q is the minimum delay of L2. And so we have a diagram here with our clock edge. Here's our clock going from 0 to 1. Q will change sometime after the clock edge. At the earliest it would change is TCCQ, and the latest it would change is TPCQ, the propagation clock to Q. And these hash lines means it could change within that time between TCCQ and TPCQ. But outside of that time, Q is stable. So we're going to define our dynamic discipline. Dynamic means signals are changing. Dynamic discipline so that the signals are valid. The sampled signals on the flip-flop are valid. So a synchronous sequential circuit must be stable. The inputs must be stable during the aperture time, the setup and hold time around the clock edge, in order for us to have valid outputs of the flip-flop. So specifically, the input has to be stable at least a setup time before the clock edge and until at least a hold time after the clock edge. So that a valid or stable sample is sampled by the flip-flop. So let's think about the delay between a pair of registers. So when we're considering dynamic discipline, we're always considering a pair of registers. And the delay between these registers has a minimum delay and a maximum delay depending on the delays of the circuit elements. So here we have register 1 and register 2, and there's some delay of the signal between those registers. And that delay is what we're going to call, or the minimum delay will be this cycle time. So let's suppose we have a clock edge. So we get a clock edge here. When is the next time we can sample, right, or get a rising edge on this clock? Well, we have to allow this signal. We get a clock edge here. The signal is going to pass through, so come out of register 1 and then go through the combinational logic and finally get put into register 2, right, that internal node of register 2 and 1, that internal node of register 2. And only at that point can we get the next rising clock edge. And so this time, at least the minimum time of that delay, is what we call the cycle time, or the clock period, right, between clock edges. So TC is the cycle time, or also called the clock period, right, the repeat time for the clock. And so we can have both minimum and maximum delays on those delays of the circuit. So we have a delay of getting our signal out of register 1. So after the clock edge, TCCQ is the minimum, TPCQ is the maximum, and then after it goes through gets out of the register 1, R1, we also have a minimum and maximum delay through the combinational logic, right? CD, contamination delay, or the maximum delay TPD. And then it takes some time to get into the circuit as well. So that's our setup time. So let's talk about the setup time constraint. This is, we have two constraints on determining whether our circuit is going to run reliably. We have the setup time constraint, and then we'll talk about the hold time constraint next. The setup time constraint depends on the maximum delay from register 1 to register 2. So remember that the input to register 2 must be stable at least a setup time before the clock edge. So we get a clock edge here, a rising clock edge, and that drives Q1 changing. So that time is the longest time that could take is TPCQ. And then Q1 changing drives a change in D2. The longest time that will take is TPD, propagation delay. And then that signal has to be at D2 at least a setup time before the clock edge so that D2 can travel or can get into the internal node of that flip-flop by the time we get the next clock edge. So we get it's right here. And so we can add this up and say the cycle time has to be greater than or equal to, well, that minimum time for the signal to travel from R1 to R2, TPCQ plus TPD plus T setup. And can it be longer? Sure, right? The signal can just be sitting here waiting inside that internal node and stable, for a longer time, but not a shorter time. And so we have our cycle time has to be greater than or equal to propagation clock to Q, time to get out of register 1, plus propagation delay, TPD, plus the setup time to get into register 2. And we can rewrite this in terms of propagation delay, because that's what we have control over, right? We have control over the design of the combinational logic as a digital designer. And so we can say, well, TPD has to be less than or equal to, we're going to take these terms and bring them over to the other side. So subtract them from both sides. So TPD has to be less than or equal to TC minus these terms, TPCQ plus T setup. And this kind of overhead, right? Ideally, we'd have the entire time, if this were 0 time and getting into the flip-flop were 0 time, would have an entire cycle time to do the work that we need to do, the calculations we need to do, right? The TPD. But we have this overhead of getting the signal out of register 1 and into register 2. And so this TPCQ plus T setup is called the sequencing overhead because of the sequencing of our inputs and of our circuit. So remember that TC, this calculation of TC is called the setup time constraint. It's also called the cycle time constraint. Now let's talk about the second constraint that we need to consider when we're doing our timing analysis, when we're figuring out if our circuit works reliably. This is called the hold time constraint. So the hold time constraint depends on the minimum delay from register 1 through the combinational logic to register 2. So the register 2 signal here, D2, has to be stable for at least a T hold after the clock edge. So in this case, we're looking at the same clock edge for R1 and R2. So here's our clock signal. We're looking at that same clock edge. And so we want to make sure that this signal does not, any signal does not get sampled. So here's our clock and race through this circuit and start changing D2 before a hold time after the clock edge, T hold. And so let's use a different color here, T hold. And so we would need to figure out, well, what's the fastest it's going to get through the circuit? Well, this is TCCQ, the earliest it would get out of register 1, plus TCD, the contamination delay, or the short path through the combinational logic. And then it could start changing the value at D2. And so if we draw this as in terms of our circuit, well, D2 could start to change as early as TCCQ plus TCD through our combinational logic. But as long as D2 doesn't start changing until after a hold time, right, we just had to keep D2 stable until a hold time after the clock edge, it's fine. So there's no violation here. So TCCQ plus TCD has to be greater than T hold, right? It can't race through and start changing at D2 before a hold time. So this is our constraint. Or you could write it another way, right? T hold is less than TCCQ plus TCD. Either way, this is probably the easier way to think about it, but you know, either it's just the same relationship. And so again, after the clock edge, we get the earliest time that the signal is going to change is a TCCQ. Right, it'll start changing Q1, and then Q1 will drive a change through the combinational logic. That earliest change is TCD, and now D2 could start to change at TCCQ plus TCD after the clock edge. And we need to make sure that that is greater than the hold time constraint where D2 had to remain stable after the clock edge. In this case, check the constraint is met. So T hold is less than TCCQ plus TCD, or again, we could have written this the other way, TCCQ plus TCD is greater than T hold. And again, rewriting this in terms of TCD, what we have control over as the circuit designer, bring this over to the other side, and we get TCD is greater than T hold minus TCCQ. So TCD is greater than T hold, and then we bring that over to the other side, minus TCCQ. So deriving it, this is the way to derive it. And then using the equation in terms of thinking about what we can control, TCD, we can use that second version of the equation. So when we're doing timing analysis to see if our circuit operates correctly, we need to calculate both constraints. The setup time constraint, also known as the cycle time constraint, and the hold time constraint. If the hold time constraint isn't met, the circuit won't run reliably at any frequency. So let's consider a circuit here. Here we have some combinational logic, and we have two registers, register 1 and register 2. We want to make sure that our setup time constraint and hold time constraints are met. So let's suppose we have the timing characteristics shown here. Our flip-flops have these timing characteristics, and our individual gates have these delays, propagation and contamination delay. So first of all, let's figure out the propagation delay and contamination delay of the circuit. Well, TPD, the longest path is going to be through either A or B through 3 gates. So TPD equals 3 times TPD gate. Well, what was that equal to? That was equal to 35, and so that's equal to 105 picoseconds. The contamination delay of the circuit is either through D to Y prime or C to X prime. So we have a single gate delay. TCD is a single contamination delay of a gate, and that was 25 picoseconds. Okay, so now that we have those, we can calculate our cycle time constraint and our hold time constraint. So cycle time constraint or setup time constraint, right, call both of those. TC has to be greater than or equal to, well, the time it takes to get out of the flip-flop, plus the maximum delay through the combinational logic, plus the time to set up into the register. Okay, so let's see, TPCQ is 50 plus 105 plus setup time was 60 picoseconds. So we're going to have 215 picoseconds. So the cycle time has to be greater than or equal to 215 picoseconds. It could be longer than that, no problem. And if later we find out, oh, hey, actually the delay of the gate was 40 picoseconds instead, right after we get the circuit back, it's actually slower than we thought, we can change that cycle time of our clock easy after manufacture. Now let's consider the hold time constraint. So the hold time constraint is, well, T hold has to be less than T contamination clock to Q plus TCD, the earliest that a signal could race out of the flip-flop and start changing the values at the input of the second bank of registers. And so we have T hold, 70 picoseconds, has to be less than TCCQ is 30 plus our TCD of our combinational logic, which is 25 picoseconds. So we have 70 picoseconds has to be less than, oh, it has to be less than 55 picoseconds. So 70 picoseconds less than 55 picoseconds. No, it's not. Right? This data could race through and start changing before the hold time constraint is met, before the register is completely stopped sampling, right? And so, yeah, this is a problem. 55 picoseconds is not greater than 70 picoseconds. Not good, right? So we have a problem here. We haven't met the hold time constraint. And the hold time constraint is actually a harder constraint to meet because if the hold time constraint isn't met, we can't increase the cycle time to make it work. We're stuck, right? And this hold time constraint, right, this is the worst case of our circuit. So even worse, it's kind of unreliable. Sometimes it works and sometimes it doesn't. And those are the worst kind of bugs because there's something changing every time you run it, or every few times that you run it. And so we need to make the short path, basically these short paths through our circuit, we need to make them longer, right? They're not long enough. They could start changing before that hold time is met. So if we add a buffer to each of those short paths, now we would have 2 gate delays for our short path, either from C to X prime or D to Y prime, and would get 2 times 25 picoseconds. So we'd get 50 picoseconds for our TCD, and then we would have 30, we still have our TCCQ of 30 plus 50. Is that greater than 70 picoseconds? Yeah, 80 is greater than 70 picoseconds. So we add buffers on that short path, and ideally it doesn't change the delay of our long path, of our critical path. In this case, it doesn't. Have to be careful there to recalculate that if you need to. But now that we have this longer delay, we have satisfied the hold time constraint and our circuit can run reliably. So remember, in timing analysis, we're always doing 2 calculations: setup time constraint and hold time constraint. Setup time constraint is also called the cycle time constraint. And if our hold time constraint isn't met, this is the other calculation, setup time constraint, doesn't make sense because our circuit won't run reliably at any frequency.